Good evening, everyone. I am Rakhi Yadav, your PMRF teaching assistant for Pericyclic Reactions and Organic Photochemistry course, which is conducted by NPTEL and whose course instructor is Professor Sankara Raman from IIT Madras. So, students, in this week 7, we are going to cover all the organic photochemistry reactions, and I hope you all have gone through Sir's lecture, so it will be easy for you to solve questions. So let's start today's class with Norrish type 1 and Norrish type 2 reaction. First of all, students, what are organic photochemistry reactions? Reactions which are driven by photochemical conditions are known as your photochemistry reactions. Since photons are involved, obviously radical will develop. So, students, in Norrish type 1 reaction, basically these reactions are reported for your carbonyl systems. Okay, so let's say photochemical conditions are given. So, in type 1 reaction, alpha cleavage occurs. Alpha. So, carbon just next to your carbonyl is this. So this alpha cleavage take place. Okay, this is your CH3 dot. Now you know that CO can also leave. Yes or no? So these two can combine and can form ethane. So basically this is your Norrish type 1 reaction. And if apart from alpha cleavage you have gamma hydrogen, alpha, beta, gamma. Hmm. Once again, let me clarify this notation. Carbon just next to carbonyl is your alpha, this is your beta, this is your gamma. Okay, so we know that there are two hydrogens present at gamma position, right? Alpha, here I was referring alpha cleavage with respect to this carbon. Okay, so in presence of H mu, it can abstract alpha hydrogen. So when H dot will leave, it will leave here radical, and this carbonyl can also be written as like this: O radical dot radical, and that H radical get abstracted by this O radical, forming into alcohol, right? Now two things can happen. One is this, that this bond can cleave and result into formation of this ketone and alkene, right? Another possibility is that these two radical can combine, right, and can form this cyclobutanol. This possibility is also there. Yes or no? So let's have a brief revision of this. In Norrish type 1 reaction, first alpha cleavage will occur, that will result into formation of radicals. Then CO will leave, okay, and then remaining radicals will recombination will occur and will form alkane. This is your Norrish type 1 reaction. In Norrish type 2 reaction, alpha cleavage can also occur as a side product, but when you are having gamma hydrogens, right, they can abstract hydrogen from there and can result into formation of this ketone and alkene, right? So let's solve question based on these reactions. So first problem for today's session is, tell order of alpha cleavage rate of following carbonyl compounds. Take your time and start solving this question. Basically, you have to tell which carbonyl compound will undergo fast alpha cleavage. Okay, you start and let me tell you. See, basically, on cleavage, it will be like this, right? So, so don't you think this cleavage rate will depend on strain of ring? Yes or no? More the strain, faster will be the rate for alpha cleavage. Therefore, order will be in same pattern A, B, C, D. Yes or no? So, correct answer to this question is, okay. The major product formed in the following reaction is, among these four options, which can be most appropriate answer? So, students, light is given, right? And you are given this starting material. If you can see, alpha cleavage can also occur. That is a one case. So, students, alpha cleavage is a one case, but we can't see anywhere that alpha cleavage product, right? So, other another possibility is this is our alpha, beta, gamma, right? And we can see that at gamma position there are two hydrogens, right? So, in presence of H mu, what can happen? These radical can form, yes or no? And if I can write it like this, alpha, beta, gamma, or this is a methyl, right? So here radical will form, yes or no? I have done nothing, just I have abstracted gamma proton. Okay. Now if you can see, these two radicals are they are energetically more favored as they can overlap from here. So, students, apart from this bond getting cleaved and resulting into formation of alkene, apart from this bond cleave, okay, what will happen is they will directly combine due to better orbital overlapping. So, correct answer is your option number 4. This is the example where uh, instead of alkene formation, actually here I have given a wrong notation. This is your alpha, beta, gamma. Okay, these will form and will result into formation of product 4. Yes or no? Okay. So students, our next reaction is dipymethane rearrangement. So, in 1967, Zimmerman first proposed this reaction, right? You just first learn how to solve this type of questions, then we will solve problems related to this reaction. So, your first task should be to identify whether this substrate is viable for this reaction. So, dipi, basically, in starting material of dipymethane rearrangement, these two double bond are not conjugated, right? They are separated by two single bonds. So, your first task is now, why this center is quaternary? Because due to presence of these two methyl groups, these are in close proximity of each other, right? So, step 1, we will do stepwise. Form radical at one side. Since this is symmetrical system, it is easy. Okay, so you have formed radical at one side. Now, what you have to do is this side can also undergo formation of radicals, right? So what it will form? Yes or no? It can form this. Now, students, you just have to remember. Listen this line carefully. You have started from here, right? Start. Now, for your easy convenience, let me tell you the side which you are started off, right? You have to cleave this three-membered ring from the side opposite to the side where you have started. I am repeating again. You have to cleave this three-membered ring to the side opposite from where you have started. So you have to start from here. Okay. And let me come back to here. Now see, if you are cleaving this bond from here, It will be as it is. Radical will be here, and this radical will combine, resulting into formation of alkene at one side. Remember, still one radical is here, and they will form your cyclopropane. Yes or no? And you can see we have drawn same product as it is given. Understood? So let me repeat. First, make radical from one side. Okay. After that, make three-membered ring by making radical from other side. Now you know that you have started from left side. So you have to break that three-membered ring from right side. Okay. Now after this, one side alkene will form, other side your cyclopropene will form. Okay. So this is the mechanism given here. First, in presence of H mu, this will undergo excitation singlet, and it will undergo singlet excitation state pi to pi star. Then, radical combination will take place, resulting into formation of the cyclopropane. Then, it can undergo rearrangement and will result into formation of this. But for problem solving, you should remember this sequence. Okay. Your homework is try to do this dipymethane rearrangement for complex strain systems such as barreling. Okay. So these are the two problems based on dipymethane rearrangements. You take 1 minute and start solving. Okay. So let me start solving for you. So now you have to choose. So students, if I ask you which radical will be stable, this one or this one? So obviously your answer would be this left side one. Okay. So radical will form here. Correct? After that, what I have told you? Formation of cyclopropane. Right? Then I have told you you have to break this three-membered ring from the side opposite to where you have started. So obviously this bond will break. Okay. Just give me 1 minute. Let me resolve this problem. I hope I'm audible now. So, students, first you have made radical from left side. So, basically, you have to now you know that this radical is there. This will combine with this, resulting into formation of olefin, and this pH radical is you stable and will result into formation of cyclo. Now I will tell you the reason why I was saying that. Please draw wait, right? Huh. So this is your final product. So students, if you have observed, obviously we will make radical first from the side which is stable. Yes or no? So in the end, we will leave that radical which is stable by itself. That's why we are cleaving this bond from opposite side. Let's say this side is not that much stable. So obviously this bond will break, will result into formation of this alkene. I hope you are getting this point. Okay. We are starting from stable side and forming and breaking that three membered ring from the side opposite to opposite to that stable side, because we know that stable side will get stabilized by itself. Okay, so your final product is this one. So by taking help of this, let's start solving question number 2 also. Obviously first radical will form at left side. Okay, so first, now you have to just break that bone. I hope you got this product. Yes or no? Let me repeat for you guys. So students, at left first in first question we have started from left side because the red. Let me use pointer for better. Huh. Among these two positions, this left side is more stable. This radical is more stable. So first we have cleaved this left side bond. Then cyclopropane formation takes place. As we know, we have started from this side. So apart from these two bonds, we are breaking this bond, because we know this radical can be stabilized by itself more than this radical. So this will form alkene from this side, and from here left side cyclopropane will form. In similar fashion, first radical will form here, okay. Then cyclopropane formation will take place, and then this side alkene will form, and from this side the cyclopropane will form. Yes or no? Okay, good. So till now we have covered two reaction. You should know. First one is your Norris type 1 reaction, second is your Norris type 2. In Norris type 1 reaction, alpha cleavage takes place with removal of CO. In Norris type 2 reaction, gamma hydrogen abstraction takes place. In gamma hydrogen abstraction reaction, there are three possibility. Sorry, basically two possibility, but three possible products. One, that directly the cyclobutanol can form. Another is formation of your ketone and alkene. Right? These were your Norris type 1 and Norris type 2 reaction. After that, we have covered dipymethane rearrangement, which was first given by Zimmerman in 1967. Basically, one non-conjugated dienes are there. Okay, and we have solved problem based on that. Now we will move ahead to Barton reaction. So before coming to Barton reaction, let me tell you how how examiner will ask to you to form this nitrile ester? Yes or no? So this can be formed from your alcohol in presence of NaNO2 in presence of HCl. You all know NaNO2 in presence of HCl will give. Okay, sorry students. Right? It will give you HNO2. And ROH, basically alcohol on reaction with HNO2 will give you RONO. Okay. Now what will happen students? Alpha, beta, gamma, delta. So here Barton reaction characteristic feature is delta hydrogen abstraction. In Norris type 2, which type of hydrogen was abstracting there? Gamma. Here, delta hydrogen abstraction takes place, and we know that NO radical, NO is stable molecule, right? So it will cleave, not stable, but this bond is most prone to cleave homolytically, right? So here O radical will come, NO radical will come. Now from gamma position, alpha, beta, gamma, delta. So from delta position, one of the hydrogen will cleave. Hydrogen will get attached to this O dot, so will form alcohol, right? Now this radical can combine with this NO radical, resulting into formation of this nitroxyl right? Via tautomerism. Now, this on hydrolysis, okay, can result into formation of your aldehyde or ketone. So basically, students, in Barton reaction, the key step is your delta hydrogen abstraction, and moreover, let me write it in this way. You just have to write if someone says you to write product directly, you just have to draw carbonyl at gamma position. Okay, and your job is done. First, examiner will ask you to form this nitrile ester by reacting it with NaNO2 and HCl, and after that you just have to abstract not gamma, delta hydrogen, and after that delta hydrogen abstraction, alcohol will form, and that first step, NO radical, right? It will combine with your that carbon radical from where delta hydrogen is abstracted, resulting into formation of oxime after hydrolysis changing to aldehyde, and this is your final product. So I hope you all have understood the mechanism of Barton reaction. So this is the problem based on your Barton reaction itself. So they are asking student the major product formed in the following reaction. So let's start solving this. Students, NOCl is given, right? H mu conditions are there. So obviously radical will form. Okay. OH is there. Okay. So we right now have studied alpha, beta, gamma, delta. Delta is here only, delta is here also. But the most accessible hydrogen is delta because it is in alignment, right? From here, first ONO will form, then O dot will form, then hydrogen will be okay. Let me write it clearly. for your understanding. In first step, ONO will form, right? H mu condition is there. It will homolytically cleave. Yes or no? Now, now this radical will be will combine with your OH with your H radical, so it will form alcohol. But students, here radical is still there, so which will combine with your NO, right? And that at last after acidic workup it will change into aldehyde. Sorry for these structures as I am drawing from my pen tab. It will form this. So correct answer to this question is option number A. Why A only? Not second, or I think not fourth, because that is not accessible hydrogen, right? So these options are wrong. So these type of problems you can face in your Barton reaction. Now the next tricky reaction of organic photochemistry is de-Mayo reaction, whose starting material is 1,3-diketone. Whose starting material is 1,3-diketone. So let me tell you how to solve problems of these reactions. So step 1. First, write enol form of 1,3-diketone given to you. Okay. Step 2 is do cycloaddition 2 plus 2. Okay. Do 2 plus 2 cycloaddition reaction between that enol formed and olefin partner. Yes or not? And last but not least, your step 3 is retroaldol. And retroaldol everyone knows, I hope. Okay. So students, let me explain you. This is your starting material, that is your 1,3-diketone. Okay, 1,3-diketone. First, it can undergo tautomerase resulting into formation of this cyclic or cyclic enone, right? Now, photochemical conditions are given to you. Under photochemical condition, it will undergo 2 plus 2 cycloaddition, resulting into formation of this cyclobutanol. Yes or no? Now, you should know this thing that in aldol, your final product is beta hydroxyketone. Here also one beta hydroxyketone. Alpha, beta, beta hydroxyketone. So, in retroaldol, what will happen? This bond will shift here, this bond will cleave and will result into formation of this 1,5-diketone. Okay, there is no other possibility than this retroaldol. So obviously it will cleave this bond from here only. So this was your de-Mayo reaction. What? First, your 1,3-diketone will undergo tautomerase, followed by 2 plus 2 cycloaddition with olefin, and then after subsequent retroaldol reaction will result into formation of 1,5-diketone. Yes or no? I hope you all have understood what is de-Mayo reaction. Nothing but it's a 2 plus 2 cycloaddition reaction between enol form of 1,3-diketone and olefin followed by retroaldol. That's all. So on basis of that understanding, try to solve this problem. Okay. Can you see anywhere 1,3-diketone? No. But you can see that one of the form is in enol already given to you, right? So your next task is to what? Cycloaddition. So students, how cycloaddition will take place? Like this. One, 2, 3, 4. Obviously, this four-membered ring will take form. So let me draw that four-membered ring. Yes or no? One, two, three, and this is your four. Okay. Now we know that at at carbon number three, one substituent is there, right? And that this is your carbon number four itself, and this bond will be there, obviously. Now this carbon number one have one extra that thing, right? This will form here. Let me number it. A. If you students, if you do numbering in these type of system, the things will become easier for you. A B C D. Understood? So after one A is coming, that is OCOPH. OCOPH. Good. And till now your job is done. Now A is there, B, C, D, and D is connected to 1. So very good. Oh, sorry for this. Okay. So now you can see this is your five-membered ring. One is your four-membered ring. Sorry. The one is your four-membered ring. This is your five-membered ring, and this one, two, three, four. One, two, three, four. So two four-membered rings and two five-membered rings are there. Okay. And one more thing. In first step, H mu cyclohexane is there. Cyclohexane is nothing but your solvent. I hope till this point you are clear. Now H2, let me draw it other way. Has someone joined? Prashant, why are you always late? You joined the class after half an hour. Okay. So basically, I have started with De-Mayo reaction in which your 1,3-diketone will undergo tautomerism, resulting into formation of this enone, right? Which will undergo 2 plus 2 cycloaddition, resulting into formation of beta hydroxy ketone that will undergo retroaldol. Okay, retroaldol from which side? See, this is your alpha beta hydroxy ketone which will undergo retroaldol, resulting into formation of this 1,5-diketone. Understood, Prashant? Okay, okay, okay. So our first example on D-Mayo reaction was this. In this system, not exactly 1,3-diketone is given, but one of the enol, you can say it. Okay. So after first reaction, that is your what? Enol form was already given. So our first task was to do intramolecular 2 plus 2 cycloaddition reaction. Okay. Now what will happen? Can you tell me? In presence of H2 or palladium carbon. Okay. But have you understood De-Mayo reaction? Okay. At last, I will quickly revise all these reactions which I have covered. So basically, students, this will become your OH. Okay. And now, see, alpha beta. Beta hydroxy is visible here. Now, acidic condition is given. In acidic condition, it will undergo retroaldol. Let me write this bond by opening it. This bond will come here. This bond will break and come here, right? And will result into formation of enol, which will further undergo tautomerism. So let's write it in proper way. This bond has cleaved, right? Here we will have ketone. Okay. Here we are having five membered ring. OH. This step is clear, Prashant. Uh, who is this other person? So finally, this system will undergo your ketoenol isomerase, okay, and will result into formation of this diketone, which will look like this. Yes or no? If you draw this, these two things are same. Let me draw here for you. Hmm. Understood? How many membered ring is there? Let's count it. One, starting from here. Okay, one, two, three, four, five, six, seven, eight, nine. And you can check here also. Starting from here. Okay, sorry. Starting from here. One, two, three, four, five, six, seven. This one is your seven membered ring that is bridged with this compound, this five membered ring. Okay, that I have not calculated here. So at last, okay, let me start it from starting. First student, 2 plus 2 cycloaddition reaction will takes place. Okay, then this OCOPH will convert into OH in this reduction condition, and after that retroaldol will takes place and will result into formation of this system. This is your example number 2. Can you write mechanism for this, Prashant, now? Your 1,3-diketone is written in its enol form. First, do cycloaddition reaction, simple cycloaddition, and then do retroaldol. You will get this product. Yes or no? Okay, let me tell you. In exam, you will get like this. In exam, you will be provided this 1,3-diketone. Okay. So first you have to write its enol form. Done. And then another olefin is given to you. You have to form. You have to do 2 plus 2 cycloaddition basically. Okay. OH will be there as it is. Now nothing, just 2 plus 2 cycloaddition reaction. Okay. And it will result into formation of this OH enol basically. This bond has cleaved right now. Yes or no? Now you can calculate the number of membered ring. One, 2, 3, 4, 5, 6, 7, 8. So here see, 8 membered ring fused with your 5 membered ring. 8 member ring fused with your 5 membered ring. Got it? Oh, we have skipped these two methyl groups. You got it, Prashant, now? Nothing. You just have to do 2 plus 2 cycloaddition followed by retroaldol. Yes or no? Okay. Our next reaction for today's session is Paterno-Bucchi reaction. So students, in Paterno-Bucchi reaction, one of your basically this is your 2 plus 2 cycloaddition only. But the thing is here another partner is your ketone. Rather than another olefin, your another partner is your ketone. So you will be provided with an alkene and a carbonyl compound, and on arrow, photochemical conditions will be provided to you. So basically, these two isomers you will get, right? Yes or no? Until and unless there is preference for one. So Prashant, tell me, are you there in class? Huh. Just help me in solving this question, okay? Let's say I have formed radical here. Now tell me, in this olefin I am numbering it A and B. Where radical will be stable, at A or B? More stable radical. Let me draw it. Which radical is stable? A radical or B radical? Why? Okay, do you know anything about hyperconjugation? Huh? N- n- Okay, but here that double bond is not there. Here radical is there. So we have to see as basically in hyperconjugation we see number of hydrogens attached to your sp2 carbon. Okay, this is your sp2 carbon due to free radical. This is your sp3 carbon. Three hydrogens are there, right? So this radical has three hyperconjugation, but this radical have six hyperconjugation. So from here, your radical B is more stable than A. Are you convinced or not? Or I should explain again. Ki why B radical is more stable than A. Moreover, you have read na 3 degree is more stable than 2 degree and 1 degree. That also is true. So in these type of reaction, what thing you have to keep in your mind that first first combine those radicals which are not stable. Among these two radicals, A star and B star, can you tell me which radical is more stable? Take your time and give answer carefully. Okay, whatever intermediates are there in organic chemistry, such as your carbocation, free radicals, these all are electron deficient. Yes or no? So they will be stabilized by your inductive effect. Inductive effect should be plus I. They will be stabilized by hyperconjugation. Moreover, they will be stabilized by resonance. Right? Among A star and B star, Prashant, which radical can be stabilized by resonance? Let me repeat question for you. Among A star and B star radical, which radical can be stabilized by resonance? Have you left the class? Prashant. Okay, let me tell you. This B radical can be stabilized by this allylic. This is allylic radical. Okay, stabilized by resonance. So obviously, if this is stable, first this will combine. Okay, this will combine with that radical which is unstable at right hand side, which is above one in comparison. And at last, these two radicals will combine. Okay. So this will be your major regioisomer that is formed in this Paterno-Bucchi reaction. Now you understood how you have to solve these type of questions. Basically, combine those two radicals first which are unstable, and then at last combine those stable radicals. Yes or no? Have you understood 20% of it, Prashant? Okay, leave. In second question again, alpha beta unsaturated ketone is given to you, right? So, if you draw radical over here, you can see that among this and this, among this is your alpha, this is your beta. This radical is quite stable because this is adjacent to your carbonyl, which is electron withdrawing, and this is your nitrile, right? So, this will be your final product. Okay. In Paterno-Bucchi reaction, nothing is there. You just have to do 2 plus 2 cycloaddition reaction between two olefins provided to you. I think last reaction of today's session is Hofmann-Loeffler-Freytag reaction. Hofmann-Loeffler-Freytag reaction. This reaction is very simple. Acidic N-chloroamines are given to you. Okay. Starting material is your N-chloro or N-haloamines. Right. In acidic condition, obviously nitrogen will be protonated. Then, under heating or thermal condition, this bond will cleave. This NX bond will cleave and will result into formation of this radical. Now, it will abstract delta, not gamma, delta. That means this is your alpha carbon, this is your beta, this is your gamma, this is your delta. Now this X dot will abstract this delta proton. right? Or we can call it 1,5 hydrogen abstraction, will result into formation of this radical. Now this radical will be quenched by Cl dot or your X dot. X is nothing but your halogen. At last, lone pair of nitrogen will knock off this X as X negative and will result into formation of cyclic amine. Yes or no? So let me restart explaining this. In basically in Hoffman-Loeffler-Freytag reaction, our starting material is N-haloamines. Okay. First, nitrogen will be protonated in acidic condition. Then, under photochemical condition, radical will form. First radical will form between nitrogen and that halogen. Okay. Then that halogen will abstract your delta proton, okay, and leave their radical. Then that radical will be quenched by X dot, because X dot are many na, from here X dot have been formed. That will be taken by your X dot. Now base is there that can abstract this proton, and then lone pair of this nitrogen can push here and result into formation of this cyclic amine. Understood? Okay. And one last reaction is also there, which is known as your Wolf rearrangement. So, students, in whenever you are given questions like this, these are known as your diazo compounds. Okay. Whenever on arrow it is written H mu, you just have to eliminate what? N2. Okay. This carbene will form. Now, for your understanding, let me explain you from basic. Student, carbene you can write is plus, 1 plus and 1 negative. This is your carbene. Okay. Now let's assume that this negative charge has gone there. Positive charge is still there. Okay. Understood? Now what happened now? When this charge came back, this bond cleave. Okay. And that negative charge will combine with this positive charge, resulting into formation of this ketene. Understood, Prashant? Carbene, you can consider it as a positive and negative charge. Now, this ketene can be further attacked by your solvent, which is here methanol. So, methanol will obviously attack at which carbon? At, at here. And after tautomerism, it will lead to formation of this ester. So, this was your Wolf rearrangement. Understood? So, have you attended that dipymethane rearrangement explanation, Prashant? Okay, I will explain again for you. Then what you have to do? This question, this one, I will solve for you, and this is your homework. Okay. In next class, ask me if you are not able to solve this. Yes or no? Why? Okay. But that will be your homework only. Okay. So, Prashant, in dipymethane rearrangement, what I have explained is you will be given two non-conjugated dienes. Okay. Now you have to start from one side. Let's say you have started from left side. Just form radicals of that olefin. Okay. Then form this cyclopropane. Now, How cyclopropane is formed? You got it. Radical radical, and that radical radical combination will take place. Now you have to break that three membered ring from that side. uh, that side should be opposite to the side from where you have started. You have started from here, so you have to break that three membered ring from this side, not from this side. Understood this thing, Prashant? So you have to break this side. After breaking this side, this radical and radical will combine and will form alkene, and this radical will combine with here and will form cyclopropane. Understood? So this was your dipymethane rearrangement mechanism. Now let's get back to the question. This question is quite difficult. That's why I have put it in last. But can you write this benzene ring like this? Yes or no? Now if you can imagine this system is nothing but your dipymethane rearrangement system. So Prashant, tell me, this is a sorry. Prashant, you can try. No matter if you are wrong, you can just try na. Tell me among from A and B position, where first radical will form in A and B. Don't you think it will form? But don't you think if first you will form here, aromaticity will break, right? So to in order to store that aromaticity, first radical will form here. Now you have to break that bond. Actually, in total, both the bonds will break, but you should know first which bond will break homolytically. Okay? Since you have started from this side, first you have made radical this side, yes or no? So you have to break that side. You can't break this bond because you have just now formed it. So after that, second bond will break from this side only. I hope you understood this thing. Good. So aromaticity will be retained. How? This radical is there, and when this radical will combine and will form this ring back. Okay. Now one radical is still there onto this carbon. Yes or no? Now nothing is left, just your radical combination will take place. This is your cyclopropane. Let me draw it clearly. Have you got this solution, Prashant? You understood? Okay. Now, Prashant, you just try to solve this question at your own. Hint, let me give you hint. Write one of this pH by opening it, okay? Write in this form. You will get system like this and will then you can start solving, okay? St- uh, try to solve. In next class, I will explain it. Just just remind me in that class, okay? This is also homework. This is quite hard. I will explain in next class. Let me write it. So, for as you have joined later, Prashant, let me give a brief recap of what I have taught in previous first half. So Prashant, I have started with Norris type 1 and Norris type 2 reaction. Okay. In Norris type 1, Prashant, kindly mute yourself. So in Norris type 1 reaction, alpha cleavage takes place. Right? So this alpha cleavage has take place and CO molecule will leave, leading to formation of this R radical. This R radical and R dash radical will combine and will result into formation of this alkane. Got it? In Norris type 2 reaction, gamma hydrogen abstraction takes place. Alpha, beta, gamma. So gamma hydrogen is there. First draw radical here. Radical, radical. This O radical will take this H dot, will form alcohol. Now, these things can isomerize in two ways. First, these radical can directly combine and will result into form of cyclobutanol. Another thing is this bond can cleave homolytically here, resulting into formation of this enol, which will tautomerize, and this radical combine, resulting into formation of this alkene. Clear? Norris type 1 and Norris type 2. Okay. Then I have solved this question. This is nothing. I have asked alpha cleavage rate. So more the strain, faster it will be ready for alpha cleavage. Yes or no? Alpha cleavage is cleavage of this bond, na. So since strain is there in this type of system, so order will be A B C D. This is the question you can see in my video whenever you will be provided with these lectures. Dipymethane rearrangement I have told you earlier also. In 1967, it was first given by Zimmerman. First, you have to make radical, then cyclopropane. Then the side from where you have started, you have to break that cyclopropane opposite side. Okay, resulting into one side formation of alkene and one side your cyclopropane. This is your dipymethane rearrangement. Then I have solved some questions. Then I have covered Barton reaction. In Barton reaction, alcohol will be given to you, which will be first treated with NaNO2 in presence of HCl, resulting into formation of this nitrile ester. This nitrile ester is going to abstract delta hydrogen. Okay, first radical formation takes place here. O dot, NO dot. Okay, this O dot will abstract delta hydrogen, resulting into formation of alcohol. Then this carbon centered radical will be abstracted by NO, resulting into formation of oxime, and oxime on hydrolysis resulted into formation of aldehyde. I am going fast because I have explained all these things. Whenever you get my videos, listen again. Okay? Huh. This was the question based on Barton reaction. So I have explained here that this axial proton is most accessible for abstraction. Therefore, only this has changed to aldehyde. Okay. Then I have covered D Mayo reaction. Here you came. So let me again repeat. Ketoenol tautomerism, 2 plus 2 cycloaddition, retroaldol, and done. Write all these reactions. You will get to know by yourself. These are the questions I have covered. This is a Paterno-Bucchi reaction, which is nothing but 2 plus 2 reaction between alkene and your carbonyl compound. These questions I covered in front of you only. Hoffman-Loeffler-Friedrich reaction is formation of cyclic amine from N-haloamines in presence of acidic condition followed by H mu. This is your Wolff rearrangement. This I have explained you. So, this is all for today's class. Thank you, Prashant, for joining. Okay. Okay, thank you.